Hey everyone, and welcome to this explainer. Consider this your absolute ultimate rehearsal space. Basically, this is your final training ground before you go in and totally ace your upcoming Grade 7 physical science assessment on the principles of energy and transformation. I am so thrilled to be your guide today. We're going to take all this source material and just break it down step by step. That way, when you finally sit down for that test, you are confident, you're prepared, and you're ready to show exactly what you know. All right, let's just dive right into it. So right out of the gate, here is the essential question for the entire unit. Where does energy go when systems change? I really want you to keep this specific question in the back of your mind throughout this whole explainer. Because on your assessment, you aren't just going to be asked to regurgitate memorized facts. You're actually going to be asked to track energy, kind of like a detective. When a system changes, like when something falls or rolls or stretches, the energy doesn't just vanish into thin air. It goes somewhere, it does something. And our main goal today is to master how to follow that trail.
Okay, here's our game plan for today. First, a quick vocabulary review. Second, we're busting the zero energy myth. Third, we'll walk through a ramp model example. And fourth, we'll wrap up with the final transfer challenge.
Kicking things off with Section 1, Energy Systems Vocabulary Review. Let's nail these core concepts.
Now, I know vocabulary can sometimes feel a little dry, but I promise you, locking in these specific definitions is literally step one to mastering your assessment. These words are the building blocks you're going to use for all your answers. So first up is kinetic energy. It's the energy an object has due to its motion. Honestly, if it's moving, it has kinetic energy. It really is that simple. I want you to visualize some everyday examples right now. A baseball flying through the air after a pitch, that's kinetic energy. A car zooming down the highway, kinetic energy. You sprinting down the hallway because you're running late for class, yep, also kinetic energy. The faster an object moves and the more mass it has, the more kinetic energy it packs.
Next, we've got potential energy. This is the energy that is stored in an object due to its position or state. And I want to put a massive, absolutely huge emphasis on that word stored. That's the real secret to understanding this whole concept. You can think of it as the energy of anticipation. It's exactly what is happening right before the movement starts. So when you pull back the string of a bow, or maybe think of a roller coaster sitting at the very peak of the track, just hanging there for a split second before the drop, that is potential energy. It has the potential to do work, purely based on where it's positioned.
It really helps to contrast these two concepts side by side, motion versus stored position, kinetic versus potential. A massive part of your assessment is going to be looking at a scenario and figuring out which of these two is at play, or how they're interacting with each other. If you can clearly cement this fundamental difference in your mind, active movement versus stored potential just waiting to happen, you're basically already halfway to an A.
Which brings us right to energy transformation. This is simply the process of changing one form of energy into another. Remember our essential question from earlier? Where does energy go? Well, it transforms. It's basically shape-shifting all around us, constantly. Think back to that roller coaster at the top of the hill. The second it drops, boom, that stored potential energy is transforming directly into the active kinetic energy of motion.
And all of that shape-shifting follows one absolute unbreakable rule of the universe, the conservation of energy. This means energy cannot be created or destroyed, it can only be transferred or transformed. You can't just magically pull energy out of thin air, and it definitely doesn't just disappear into the void. Assuming there's no friction in the mix to complicate things with heat, the total mechanical energy in a closed system stays perfectly constant. You always have the exact same total amount of energy at the end as you did at the beginning. It just might be wearing a slightly different disguise.
Moving right along to Section 2, Busting the Zero Energy Myth. Please don't fall for this trap.
Okay, consider this a massive pro tip from me to you. Assessments love to test not just what you know, but whether you can spot common misconceptions. And there is this one classic trap that catches so many students when they're rushing through a test, which is confusing potential energy with kinetic energy. We need to make sure you don't fall for it. You are very likely going to see a question that tries to trick you into agreeing with this statement, it's not moving, so it has zero energy. They'll usually give you a scenario like a boulder sitting right on the edge of a cliff, or maybe a heavy book resting on a high shelf. The test is trying to see if you think that just because the kinetic energy is zero, because the object is completely stationary, that the total energy must also be zero. The second you see this on your exam, alarm bells should be ringing in your head.
So how do we systematically dismantle that myth? With evidence, of course. Point 1. Gravitational potential energy absolutely exists at rest. Because that book is high up on the shelf, gravity is actively pulling on it.
It is totally loaded with stored energy just waiting to be unleashed. Point 2. The exact millisecond it falls off that shelf, all that potential energy instantly starts converting right into kinetic energy. And point 3. Thanks to our good friend, the conservation of energy, the total mechanical energy remains completely constant throughout the whole process. So, that stationary object high up, it's practically bursting with energy. It's just stored. Boom, myth busted.
All right, section 3, ramp model worked example. Let's start visualizing the transformation.
Now it's time to actually put these rules into practice. I like to call this the game tape segment of the explainer. We're going to look at a super classic, highly typical assessment model, which is a ball and a ramp, and I'm going to model exactly how you should think through it. So, we've got 3 distinct stages of the ball's physical journey. Step 1, the ball is at the very top of the ramp. Step 2, the ball is partway down. And step 3, the ball is at the very bottom. When you get a question like this, you need to use a think aloud strategy in your head. Ask yourself, okay, what is the ball doing right now? Where is it located? Is it moving? Let's apply our new vocabulary to these 3 specific steps.
This table brilliantly illustrates the exact thought process you need to have. Let's look at the top position. The ball is at its absolute highest point, so its potential energy is high. But it hasn't started rolling quite yet, so its kinetic energy is basically 0. Now check out the middle. As it rolls down the ramp, it's losing some of that height, but it's gaining speed, right? So the potential energy drops down to medium, and the kinetic energy rises up to medium. Finally, at the bottom, it has literally no more height left to fall from, so potential energy is low or 0, but it's moving at its absolute fastest, so the kinetic energy is high. This data perfectly reveals an inverse relationship. As potential goes down, kinetic goes up. It is just a perfect, beautiful demonstration of the conservation of energy right in action.
Finally, section 4, the final transfer challenge. It's time to apply what you've learned.
Okay, this right here is the final boss of our rehearsal today. On an actual assessment, teachers don't just want you to memorize that ramp example we just did. They really want to see if you can take the logic and the rules we've been practicing and transfer them over to a brand new everyday scenario. So imagine you're holding a tightly stretched rubber band. You're holding it completely still, and then you let it go. What are the exact energy transformations taking place there? Where does the energy go when this system changes? I want you to think about what kind of stored energy it has right before you release it. Then think about what happens the exact millisecond it leaves your fingers. I want you to trace that energy. If you can clearly explain the transformation happening in that rubber band using all the vocabulary we reviewed today, then you are more than ready for this assessment. Good luck with your review, keep tracking that energy, and I will see you in the next explainer.